All right, testing my mic here. Okay, that sounds good to me. And let us begin. So, welcome back to my stream. As always, we're gonna continue with our Pytorch course as usual. And yeah, it's a brand new day, and I'm excited to learn brand new things. All right, let's start. So, is my screen visible? Yeah, it is. So yesterday we left off at CNN's. We we were trying. Well, we left off at the spot where Daniel here was trying to train the visual neural network, CNN, convolutional neural network. I I think that's what it stands for, at least from memory. Anyhow, let me just skip to that part here. So we were at were we at 88? No, we didn't reach here now. Um, let's see. I think this is the part. Ah, yeah, this is the part. All right, we are about to start creating the training and testing loop for our model here. Let's start. Okay, let's begin. My camera is a bit slanted, isn't it? Let me fix that. So I made it more slanted. Uh, that should be good enough. Great. Let's continue. Hmm. All right. That's another module I didn't know about. Hmm. That's the smart way of doing it. We divided by 32 then? Is that what you said? Yep. 32 in this case. Here's a tidbit. If you use so enumerate by default starts with the first number as 0. It follows 0 indexing. So if you provide a keyword argument called start, you can provide what number you want to output. So rather than it starting from 0, it will start from 1 now. And in a lot of cases that makes more sense. Right. Yeah, so we have more possibilities of more number crunching, which would in turn provide us with better results. So the advantage is twofold. What does it say? Look at batch times len of x. Okay, let's just read and it. Samples. Yeah, if yeah, okay, that makes sense. Okay, why are we dividing the number? Looked at so the number of the nth batch that we're on. Let's say we're on the 400 batch. We multiplied with the number of elements that we have in each batch, which is 32. But then why are we dividing it? Is what I don't understand. I should tell you how many samples we looked at, right? Anyway, let's just code it out. We understand once this thing runs. Exciting indeed. Hmm. What is length of x going to equal? Okay, let's just go through this. We'll understand. No, we didn't. Alright. Yep. Right, right. Okay, that makes sense. We need to do dot device, right? Nah, we need to do dot device. Hmm. Why isn't he doing dot device? There. Pretty sure we need to. Anyhow, let's just do this. Write this out. Remember, when in doubt, got it out. I should make that my motto. Yeah, we need to do device there. Oh, I mean out, right? Dot device. Yeah, there we go. Alright, we figured that out before that. Yeah. Yep. Yes, because code always works the first time. Where did I hear that? I think it's from Mark Rober video where he created a robot which could do jigsaw puzzles. Let's try to figure it out by ourselves first. Oh, this won't work. Yeah, well, for not for that reason. We need to run all these cells before this, don't we? Let's do one thing. Let's just come here and click run all. Okay, let that do its processing. That's a lot of cells out there to process. We have a typo here to this one, definitely run. All right. Yeah, we have reached there. So let's run the now. Nope. Another typo. We have any other typos here? No, we don't. So let's try running that. What single is not allowed? Hmm. Single bracket is not. But oh, okay. Yeah. There we go. That should fix that. Hopefully. Yeah. Yep. We made some mistake there with the calculations. Um. Let's try to figure it out ourselves. Ha, ha, ha. Looked at, let's see here. The print looked at batch times line of x divided by, we need to put this in brackets, don't we? And before I run it, let me just go and create the model again, the instance of the model again, which I should be able to do so by coming here and let's run that. Let's also run our loss function and optimizer. Let's instantiate them again. Although where would I get them? Let's just control F and search for it. There we go. Alright, cool. In that case, let me run this and hopefully, nope, didn't work. Stop that, stop that. Yeah. Look that batch into line of X. Line of train data loaded or data set batch times len of X. Hmm. What might be happening here in that case? We have X, we have Y. Hmm. Could it be because I gave a start? Maybe. Maybe let's just check. Nope, not that. Looked at batch times len of X. Oh, of course, of course. Our hunch was right. We just looked at it the wrong way. We just have to multiply this to get the number of samples, number of samples. And then this just for representing like these two things are separate. It's not one gigantic mathematical equation. Um, should be good. And let's go up and just run this. And not that, let's just create the model first and then run it. Create the model there, create the loss function and optimize it again, and then run the training loop. And there we go, it started. Mhm. It is, isn't it? But I mean, it's for learning purpose, so it's all right. Yep, because we'll pass that in a function. Now I don't think there are any typos this time, which is good. And let's just call this function now. See whether that works. Moral name, loss, and hmm. Are those? Okay, something's wrong. Yeah, something's wrong. Yeah, probably messed something up with the calculation. There should be hmm. Okay. All right. Something's wrong. Yeah, this needs to take one step back. That's all. This needs to take one step back. Yeah, that should result in. Okay, that looks better. Ah, we can do that. All right. All right. Ah, look at that. We have someone watching my stream. Hey, to whoever came just now. Feel free to ask any questions in the chat. PQDM is really useful. I didn't know. I'm gonna use it in most of my projects from now on. And I'm gonna enable the GPU here, but I'm just gonna write the device agnostic code anyways. Geez, I can't type else. Whoa, that's a sudden increase in viewer count. Hi to whoever just came to my stream right now. No, we can't. We need the what's it? Relu layer. Yep. I think it's to do with this isn't in a circle exactly. So for most of the cases, I would imagine linear lines to work pretty good. But if we combine that with curves and everything, it would at least my prediction is that it should be more accurate. So let's see. Uh-huh. Now Daniel is just repeating what I just mentioned right now. Let's do that on a new chord block. Yep. And why do we want to flatten it? Because I like to think of it as in this scenario we are using a grayscale image. So n- in the scenario where we do use RGB, you know, images with color and actual normal image, we can split it into three images. So flattening it would just give us three arrays, uh, each for red, blue, green, filled with however many pixels there are. Anyhow, let's continue with the tutorial. Are we gonna do the same layers, or I mean, we are gonna add Relu layers here, but how many? Let's just continue through the video a bit. Right. In features needs to be hidden unit. Or is it because we're flattening the entire thing first? Oh, that's alright, but then. Ah, yeah, of course, okay, never mind. This is supposed to be input shape itself, hidden unit. Then we're gonna put relu layer in between that. We could have done one more layer, but I guess it's alright. Let's see what this thing is capable of now. And to end it, let's do. Yeah, we need to do another. Oh, never mind. He has given output shape here. What? Oh, yeah. There we go. That should fix that. Let's just create the forward method real quick. Take the next, which is tensor, and it returns the layer stack, whatever the layer stack outputs. Yep, yep. It should be return on returns, and that valid syntax. Perhaps you forgot a comma. Did I use a period here or something? What's happening here? Oh yeah, we need a comma here. Yep, there we go. Uh-huh. I made a typo there again. Input shape 784. Why 784? Because our image is 28 pixels across and 28 pixels wide, which results in the input shape being 28 times 28, which is equal to 784. Alright, let's do that. I definitely need to get some kind of air cooler in here. I can't turn on the fan, otherwise my mic would just, yeah, the audio would be terrible if I turn on the turn on my fan. Anyhow, output shape. What's output shape supposed to be? It's 9 in this case. Not 9. It's 10 in this case because we have that many possibilities. But to make that dynamic, let's do it this way. I guess. Len of class names to device. Wait, what is it doing? Just len of class name should be enough. Why is it doing to device though? I think he gave an explanation here in me. Let's just go a bit backwards. Oh, we're send. Okay, I see. We are gonna send the model to the target device, not the enough class names. That would be wait, that would have been weird. Anyhow, we don't need to check then since we're just using the CPU anyhow.
go ahead and try to create a loss function for our model and optimize.
I just realized my desktop audio was turned off till now. That would yeah, there's nothing I can do about it now. Although my mic was turned on, yes, that's good.
Optimizer for model 1. The hint is that they can be the exact same loss function and optimizer as model 0. So give that a shot, and I'll see you in the next video. Welcome back. In the last video, we created another model, so we're continuing with our modeling experiments. And the only difference here between Fashion MS Model V1 and V0 is that we've added in nonlinear layers. Now, we don't know for now. We could think or guess whether they would help improve our model. And with practice, you can start to understand how different functions will influence your neural networks. But I prefer to, if in doubt, code it out, run lots of different experiments. So let's continue. We now have to
that's our motto
loss
too.
function,
If in
loss,
doubt,
optimizer, and evaluation metrics. So we've done this for model 0. So we're not going to spend too much time explaining what's going on here. And we've done this a fair few times now. So from helper functions, which is a script we downloaded before, we're going to import our accuracy function. And we're going to set up a loss function, which is we're working with multi-class classification. So what loss function do we typically use? And then dot cross entropy loss. Yep. And as our optimizer is going to be torch.optim.sgd. And we're going to optimize this time. I'll put in the params keyword here. Model 1.parameters. And the learning rate, we're just going to keep it the same as our previous model. And that's a thing to keep a note for your experiments. When you're running fair few experiments, you only really want to tweak a couple of things or maybe just one thing per experiment. That way you can really narrow down what actually influences your model and what improves it / what doesn't improve it. And a little pop quiz. What does the loss function do? This is going to measure how wrong our model is. And what does the optimizer do? Tries to
optimizes the number
models parameters
in each
reduce the loss.
Batch.
So that's what these two functions are going to be doing. The accuracy function is, of course, going to be measuring our model's accuracy. We measure the accuracy because that's one of the base classification metrics. So we'll run this. Now what's next? We're getting quite good at this. We've picked a loss function and an optimizer. Now we're going to build a training loop. So we'll run this. Now what's next? We're getting quite good at this. We've picked a loss function and an optimizer. Now we're going to build a training loop. However, we spent
why doesn't Google why doesn't Colab recognize our helper function module though? I wonder.
Anyhow, that in a previous video, if we go up here, that was our model function. Oh, that was helpful. We turned it into a function. How about we do the same with these? Why don't we make a function for our training loop as well as our testing loop?
Finally, we're gonna make it into a function.
So I think you can give this a go. We're gonna make a function in the next video for training. We're gonna call that train step. And we'll create a function for testing called test step. Now they'll both have to take in some parameters. I'll let you figure out what they are, but otherwise we're going to code that up together in the next video. So I'll see you there.
The loss function,
and what's our next step? Well, let's create training and evaluation loops. So let's make a heading here. I'm going to call this functionalizing training and evaluation or / testing loops because we've written similar code quite often for training and evaluating / testing our models. Now we're going to start moving towards functionalizing code that we've written before because that's not only a best practice, it helps reduce errors because if you're writing a training loop all the time, we may get it wrong. If we've got one that works for our particular problem, hey, we might as well save that as a function so we can continually call that over and over and over again. So how about we, and this is going to be very rare that I'm going to allow you to do this, is we're going to copy this training, and you might have already attempted to create this. That is the function called, let's create a function for one training loop, and we're going to call this train step. And we're going to create a function for the testing loop. We're going to call this test step. Now, these are just what I'm calling them. You can call them whatever you want. I just understand it quite easily by calling it train step, and then we can, for each epoch in a range, we call our training step. And then the same thing, for each epoch in a range, we can call a testing step. This will make a lot more sense once we've coded it out. So let's put the training code here. To functionize this, let's start it off.
Let's just copy it. Where's our training loop? Yep, this is our training loop. Although we didn't copy it correctly, like we need to copy the entire thing now.
With train step. Now, what parameters should our train step function take in? Let's think about this. We need a model, we need a data loader, we need a loss function, and we need an optimizer. We could also put in an accuracy function here if we wanted to, and potentially, it's not here, but we could put in what target device we'd like to compute on and make our code device agnostic. So this is just the exact same code we went through before. We loop through a data loader, we do the forward pass, we calculate the loss, we accumulate it, we zero the optimizer, we perform backpropagation in respect to the loss with the parameters of the model, and then we step the optimizer to hopefully improve the parameters of our model to better predict the data that we're trying to predict. So let's craft a train step function here. We'll take a model, which is going to be torch nn.module, type hint, and we're going to put in a data loader, which is going to be of type torch utils.data.data loader. Now, we don't necessarily need to put this in, these type hints, but they're a relatively new addition to Python, and so you might start to see them more and more, and it also just helps people understand what your code is expecting. So the loss function, we're going to put in an optimizer, torch.
Yeah, I'm a person who likes
we also want an accuracy function. We don't necessarily need this.
Literally document every single piece of code. There's a saying. Oh, I don't know who I got this from. Probably some YouTube tutorial. Probably from some YouTube tutor itself. But what was the saying again? Yeah, Wait, let me just remember that. Let me just remember. Wait, let me just try to remember. Yeah, for the first few months that after you've written your code, you and God understand your code perfectly, but after that, only God knows what you've written. So remember, always document your code. Um, yeah, just like let's just continue with the tutorial here. We have a loss function.
Nice to haves. The first four are probably the most important.
Loss functions are a child of modules. Okay, of the module class. I didn't know that. Anyhow, optimizer. I guess it makes sense because at the end of it, our loss function is just a couple of layers just punched in together, right, with the forward method.
And then device. So torch is going to be torch.device equals device. So we'll just hard code that to be our already set device parameter. And we'll just write in here, performs training step with model trying to learn on data loader. Nice and simple. We could make that more explanatory if we wanted to, but we'll leave it at that for now. And so right at the start, we're going to set up train loss and train ac equals 0, 0. We're going to introduce accuracy here. So we can get rid of this. Let's just go through this line by line. What do we need to do here? Well, we've got for batch xy in enumerate train data loader, but we're going to change that to data loader up here. So we can just change this to data loader. Wonderful. And now we've got model 0.train. Do we want that? Well, no, because we're going to keep this model agnostic. We want to be able to use any model with this function. So let's get rid of this model.train. What we are missing one step here is put data on target device. And we could actually put this model.train up here. Put model into training mode. Now this will be the default for the model, but just in case, we're going to call it anyway, model.train. Put data on the target device. So we're going to go x, y equals x.to device, y.to device. Wonderful. And for pass, we don't need to use model 0 anymore. We're just going to use model that's up here. The loss function can stay the same.
Although what's wrong here? Did we miss? Yeah, we missed comma here, didn't we? It should be resolved now. So we set our model to model.train.
Because we're passing in a loss function up there. The train loss can be accumulated, that's fine. But we might also
Yep, let's send our features and labels to the target device. Gotta make it device agnostic.
also accumulate now the train accuracy. Calculate loss.
Gotta remove that 0 from that.
And accuracy per batch. So train ac equals or plus.
Train accuracy plus is equal to accuracy of
equals our accuracy function on y true.
Okay, we just went to code box up for some reason. Yeah. Yeah, there we go. Let's call our accuracy function here.
Equals y, and y pred equals y pred. So the outputs here, y pred, we need to take, because the raw outputs the raw logits from the model, because our accuracy function expects our predictions to be in the same format as our true values, we need to make sure that they are. We can call the argmax here on the first dimension. This is going to go from logits to prediction labels. We can keep the optimizer 0 grad the same, because we're passing in an optimizer up here. We can keep the loss backwards because the loss is just calculated there. We can keep optimizer step, and we could print out what's happening, but we might change this up a little bit. We need to divide the total train loss and accuracy. I just want to type in accuracy here because now we've added in accuracy metric. Ac. So train ac divided equals length train data loader. Oh no, sorry. We can just use the data loader here. Data loader. Data loader. And we're not going to print out per batch here. I'm just going to get rid of this. We'll make at the end of this step, we will make a print out here. Print. Notice how it's at the end of the step because we're outside the for loop now. So we're going to, here we're accumulating the loss on the training data set and the accuracy on the training data set per batch. And then we're finding out at the end of the training step, so after it's been through all the batches in the data loader, we're finding out what the average loss is per batch and the average accuracy is per batch. And now we're going to go train loss is going to be the train loss on 0.5 and then we're going to go train ACK is going to be train ACK, and we're going to set that to 0.2f.
Alright, let's just write that print statement here.
Get that there. Percentage.
Let's also put percentage.
Wonderful. So if all this works, we should be able to call our train step function and pass it in a model, a data loader, a loss function, an optimize, an accuracy function, and a device. And it should automatically do all of these steps. So we're going to find that out in a later video. In the next video, we're going to do the same thing we've just done for the training loop with the test step. But here's your challenge for this video, is to go up to the testing loop code we wrote before and try to recreate the test step function in the same format that we've done here. So give that a go, and I'll see you in the next video. Welcome back. In the last video, we functionalized our training loop. So now we can call this train step function, and instead of writing all this training loop code again, well, we can train our model through the art of a function. Now, let's do the same for our testing loop. So I issued you the challenge in the last video to give it a go. I hope you did, because that's the best way to practice Pytorch code.
Alright, let's do that first. Let's have a test. Yep. This takes in the model and what? Well, let's just put in the code here, and then we can just fill in for all we need. So we have our model. Nope. Yep. And then we have our data loader. We can just call it test data loader. And then
Right? More Pytorch code. Let's put in a model, which is going to be torch and then .module. And we're going to put in a data loader, because we need a model and we need data. The data loader is going to be, of course, the test data loader here, torch.utils.data.data loader. And then we're going to put in a loss function, which is going to be torch and then.module as well, because we're going to use and then cross entropy loss. We'll see that later on. We're going to put in an accuracy function. We don't need an optimizer because we're not doing any optimization in the testing loop. We're just evaluating. And the device can be torch.device, and we're going to set that as a default to the target device parameter. Beautiful. So we'll put a little doctrine here. So performs a testing loop step on model going over data loader. Wonderful. So now let's set up a test loss and a test accuracy, because we'll measure test loss and accuracy with our testing loop function. And we're going to set the model into, I'll just put a comment here, put the model in eval mode. So model.eval. We don't have to use any underscore here, as in model 0, because we have a model coming in the top here. Now, what should we do? Well, because we're performing a test step, we should turn on inference mode. So turn on inference mode context manager. Remember, whenever you're performing predictions with your model, you should put it in model.eval, and if you want as many speedups as you can get, make sure the predictions are done within the inference mode, because remember, inference is another word for predictions, within the inference mode context manager. So we're going to loop through our data loader for x and y in data loader. We don't have to specify that this is x test or y test. We could want to, but because we're in another function here, we can just go for x, y in data loader. We can do the forward pass after we send the data to the target device. Device. So we're going to have x, y equals x.to device, and the same thing with y. We're just doing best practice here, creating device agnostic code. Then what should we do? Well, we should do the thing that I said before, which is the forward pass. Now that our data and model will be on the same device, we can create a variable here, test pred equals model. We're going to pass in x, and then what do? We can calculate the loss. So to calculate the loss / accuracy, we're going to accumulate it per batch. So we'll set up test loss equals loss function, plus equals loss function. We're going to pass it in test pred and y, which is our truth label, and then the test act where you will accumulate as well. Okay. Using our accuracy function, we'll pass in y true equals y, and then y pred. What do we have to do to y pred? Well, our test pred, we have to take the argmax to convert it from, so this is going to outputs raw logits. Remember, a model's raw output is referred to as logits. And then here, we have to go from logits to prediction labels. Beautiful. Oh, little typo here. Did you catch that one? Tab. Beautiful. Oh, look how good this function is looking. Now, we're going to adjust metrics. So adjust metrics and print out. You might notice that we're outside of the batch loop here, right? So if we draw down from this line 4, and we write some code here, we're still within the context manager. This is important because if we want to adapt a value created inside the context manager, we have to modify it still within inside that context manager. Otherwise, Python will throw an error. So try to write this code if you want outside the context manager and see if it still works. So test loss, we're going to adjust it to find out the average test loss and test accuracy per batch across a whole step. So we're going to go length data loader. Now we're going to print out what's happening. Print out what's happening. So test loss, which we put in here, we're going to get the test loss. Let's get this to 5 decimal places. And then we're going to go test ACK, and we will get that to 2 decimal places. You can do this as many decimals as you want. You can even times it by 100 to get it in proper accuracy format. And we'll put a new line on the end here. Wonderful. So now it looks like we've got functions. I haven't run.
Let's do that.
it in proper accuracy format.
Gosh, it's getting too hot here. The sun is just. You know what? I just gotta turn on the fan. Hopefully, let's. Oh no, that sounds. Yeah, that doesn't sound the best, does it? Oops. I definitely need to change to air cooler. For the timing, I guess it's fine. Oops. Yep. Yep. Yeah, let's set that to where it was before. Okay, let's just run through this. Once the sun goes down a bit, I'll turn off the fan. I apologize in advance for the noise here.
And we'll put a new line on the end here. Wonderful. So, now it looks like we've got functions, I haven't run this cell yet, for a training step and a test step. So how do you think we could replicate, if we go back up to our training loop that we wrote before, how do you think we could replicate the functionality of this, except this time using our functions? Well, we could still use this for epoch and TQDM range epochs, but then we would just call our training step for this training code, our training step function, and we would call our testing step function, passing in the appropriate parameters, for our testing loop. So that's what we'll do in the next video. We will leverage our two functions, train step and test step, to train model 1. But here's your challenge for this video. Give that a go. So use our training step and test step function to train model 1 for 3 epochs. See how you go, but we'll do it together in the next video. Welcome back. How'd you go? Did you create a training loop or a Pytorch optimization loop using our training step function and a test step function? Were there any errors? In fact, I don't even know. But how about we find out together? Hey, how do we combine these two functions to create an optimization loop? So I'm going to go torch.manualseed 42, and I'm going to measure the time of how long our training and test loop takes. This time we're using a different model. So this model uses non-linearities and it's on the GPU. So that's the main thing we want to compare is how long our model took on CPU versus GPU. So I'm going to import from timer, import default timer as timer, and I'm going to start the train time. Train time start on GPU equals timer, and then I'm just right here, set epochs. I'm going to set epochs equal to 3 because we want to keep our training experiments as close to the same as possible so we can see what little changes do what, and then it's create a optimization and evaluation loop using train step and test step. So we're going to loop through the epochs, or epoch in TQDM, so we get a nice program.
I mean, we don't have to define that again, do we? Because we already have defined it, I believe. We can just call it start time and end time. We don't need to give it that huge of a variable name. Yeah, let's just do start time. I guess he's doing this to show us the difference between the code being run on a GPU and a CPU. But since we're already now running it on a CPU, let's just stick to a shorter variable name.
Then we're going to print epoch, a little print out of what's going on, epoch, and we'll get a new line, and then maybe 1, 2, 3, 4, 5, 6, 7, 8 or something like that. Maybe I miscounted there, but that's alright. Train step, what do we have to do for this? Now,
Oops, let me plug in my lab here, otherwise it will shut off. I'll be back. I can't even see my laptop screen right now because of this. Let me just tilt this here a bit. That should be good. And yeah, did you miss me? Let's continue.
We have a model. What model would we like to use? We'd like to use model 1. We have a data loader. What data loader would we like to use? Well, we'd like to use our train data loader. We also have a loss function, which is our loss function. We have an optimizer, which is our optimizer. And we have an accuracy function, which is our accuracy function, and oops, forgot to put fn. And finally, we have a device which equals device, but we're going to set that anyway. So how beautiful is that for creating a training loop? thanks to the code that we functionized before. And just recall, we set our optimizer and loss function in a previous video. You could bring these down here if you really wanted to, so that they're all in one place. Either way up, but we can just get rid of that because we've already set it. Now, we're going to do the same thing for our test step. So what do we need here? Let's check the doc string. We could put a little bit more information in this doc string if we wanted to really make our code more reusable, so that if someone else was to use our code or even us in the future knows what's going on. But let's just code it out because it's still fresh in our mind. Model equals model 1. What's our data loader going to be for the test step? It's going to be our test data loader. Then we're going to set in a loss function, which is going to be just the same loss function.
It's gonna pass in the same variable names except replace data loader with test data loader.
Anyway, look at that. Our whole optimization loop in a few lines of code. Isn't that beautiful? So these functions are something that you could put in, like our helper functions.py, and that way you could just import it later on, and you don't have to write your training loops all over again. But we'll see more of an example of that later on in the course. So let's keep going. We want to measure the train time, right? So we're going to create, once it's been through these steps, we're going to create train time end on CPU, and then we're going to set that to the timer. So all this is going to do is measure a value in time once this line of code is run. It's going to run all of these lines of code, so it's going to perform the training and optimization loop, and then it's going to, this should be GPU. It's going to measure a point in time here. So once all this code's run, measure a point in time there, and then finally we can go total train time for model 1 is equal to print train time, which is our function that we wrote before, and we pass it in a start time, and it prints the difference between the start and end time on a target device. So let's do that. Start equals what? Train time start on GPU. The end is going to be train time end on GPU, and the device is going to be device. Beautiful. So are you ready to run our next modeling experiment, model 1?
Wait a second, let me just write this out real quick and then we'll start. And there's gonna be end time, and device is of course gonna be device.
On the GPU, and it's using nonlinear layers, and we want to compare it to our first model, which our results were model 0 results. And we have total train time on model 0, yes we do. So this is what we're going for. Does our model 1 beat these results, and does it beat this result here? So 3, 2, 1, do we have any errors? No we don't. Okay, train step got an unexpected keyword loss. Oh.
It's supposed to be loss function.
Let's run it again. There we go. Okay, we're running. We've got a progress bar. It's going to output at the end of each epoch. There we go. Training loss. All right. Test accuracy. Training accuracy. This is so exciting. I love watching neural networks train. Okay, we're improving per epoch. That's a good sign. But we've still got a fair way to go. Oh, okay. So what do we have here?
When we supposed to give model 1? What's happening here? Test step got an unexpected keyword argument loss. I guess we have to let's see if this is running. Yeah, no. This is optimize. Right, that is what it's supposed to be. We don't need an optimizer here. Okay, accuracy function, we still need accuracy function and device. Let's just go back and create our model again and call our loss function and optimizer again and run our loop. We should hopefully run now. Let's see. Fingers crossed this works. Let's see. Tesla's reference before assignment inline into step. Okay. Tesla's reference before assignment. But I said this is 0 first, right? Run that. You can go back, run this, and then run our and our loop, which should run now. Let's see. And it's running. Nah, what happened here? Expected input batch size 16 to match target batch size 32. Where exactly did we now get that? Test predictions and why? Alright. What's happening here?
Well, okay, we're improving. There we go, training loss function. It's good. It's going to do is measure value in time.
Now.
A whole optimization loop in a few lines of code.
Go back.
You could cal function and oops, what looks like we've got functions. I haven't run this cell yet. For a training step and a test step. So how do you think we could replicate if we go back up to our function? We'll leave step 42.
Let's just follow that.
TQDM is going off. Train what data miser. Accurate. So good. Next more. Model equals and loops all over again. In time, right? So what this is going to do is measure it. It'll train time. Time. GPU. Device. And it's using so type. There we go. Training loss. Let's run it again. There we go. Train step got an unexpected. These results. Loss. Oh. We have some. And it's we have an optimizer.
So we need to definitely go back and check this out.
Leave it and we would call that. Let's train loop code again. Well, we can train our model through Pytorch code is to run function. We're going to put in a default on model going over data loader. Wonderful. So now let's set up a test last step because we have a model coming in the top here. Now, what should we do? Well, because we're performing test step, we should turn on inference mode. So turn on inference mode context manager. Remember, whenever you're performing predictions with your model, for instance, specify that we get y equals next, got to device, and the same thing with y. We're just doing best practice here, creating device agnostic code. Then what should we do? Well, we should do the thing that I said before, which is the forward pass. Now that our data and model will be on the same function, plus equals loss function. We're going to pass it in test spread and y, which is our truth label, and then the test act where you will accumulate as well using our accuracy function.
This should be model. Run that again and go up and then create a model, define loss and optimizer again, and then if you run the loop, this should run this time. What now?
We'll pass in y true equals y, and then y pred. What do we have to do to y pred? Well, our test spread, we have to take the argmax to convert it from, so this is going to outputs raw logits. Remember, a model's raw output is referred to as logits, and then here we have to go from logits to prediction.
That's why. Okay, again, let's just go up, run this, run this again just in case, and then run this. Hey, there we go. Finally, we got it to work.
Labels. Beautiful. Oh, little typo here. Did you catch that one? Tab. Notice that because we're going to adjust it to find out decimal colors. Now, function we will leverage out to SK. I don't even know. So let's make it and also we'll print out what's going to be. Beautiful. Do we have? Let's run it again. Test accuracy, training accuracy. This is so exciting. I love watching neural networks train. Okay, we're improving per epoch. That's a good sign.
Yeah.
But we've still got a fair way to go. Oh, okay. So what do we have here? Well, we didn't beat our. It looks like we didn't beat our model 0 results with the non-linear layers.
That's right.
We only just slightly had a faster training time. Now again, your numbers might not be the exact same as what I've got here, right? So that's a big thing about machine learning is that it uses randomness, so your numbers might be slightly different. The direction should be quite similar, and we may be using different GPUs, so just keep that in mind. Right now, I'm using a NVIDIA SMI. I'm using a Tesla T4, which is, at the time of recording this video, Wednesday, April 20, 2022, is a relatively fast GPU for making inference. So just keep that in mind. Your GPU in the future may be different, and your CPU that you run may also have a different time here. So if these numbers are like 10 times higher, you might want to look into seeing if your code there's some error. If they're 10 times lower, well, hey, you're running it on some fast hardware. So it looks like my code is running on CUDA slightly faster than the CPU, but not dramatically faster. And that's probably akin to the fact that our dataset isn't too complex and our model isn't too large. What I mean by that is our model doesn't have like a vast amount of layers, and our dataset is only comprised of, like this is the layers our model has. And our dataset is only comprised of 60,000 images that are 28 by 28. So as you can imagine, the more parameters in your model, more features in your data, the higher this time is going to be. And you might sometimes even find that your model is faster on CPU. So this is the train time on CPU. You might sometimes find that your model's training time on a CPU is, in fact, faster for the exact same code running on a GPU. Now, why might that be? Well, let's write down this here. Let's go note. Sometimes.
Is it with the way that a GPU is better for like normal math, right? Like for just additions, arithmetic, and stuff. Like when you have lots of it, that's why we use GPUs in gaming, because there's just too many numbers that you have to add, subtract, and stuff. But CPU is better for doing more complicated math, even though it can only do less amount of it parallelly compared to a GPU. Is that it?
Depending on your data / hardware, you might find that your model trains faster on CPU than GPU. Now, why is this? So one of the number one reasons is that, one, it could be that the overhead for copying data / model to and from the GPU outweighs the compute benefits offered by the GPU. So that's probably one of the number one reasons, is that you have to, for data to be processed on a GPU, you have to copy it because it is by default on the CPU. If you have to copy it to that GPU, you have some overhead time for doing that copy into the GPU memory. Okay. And then although the GPU will probably compute faster on that data once it's there, you still have that back and forth going between the CPU and the GPU. And the number two reason is that the hardware you're using has a better CPU in terms of compute capability than the GPU. Now this is quite a bit rarer. Usually if you're using a GPU like a fairly modern GPU, it will be faster at computing deep learning or running deep learning algorithms than your general CPU, but sometimes these numbers of compute time are really dependent on the hardware that you're running. So you'll get the biggest benefits of speed ups on the GPU when you're running larger models, larger data sets, and more compute intensive layers in your neural networks. And so if you'd like a great article on how to get the most out of your GPUs, it's a little bit technical, but this is something to keep in mind as you progress as a machine learning engineer, is how to make your GPUs go brr, and I mean that brr, from first principles. There we go. Making deep learning go brr, as in your GPU is going brr because it's running so fast.
I don't know, just
so this is by Horace.
with that.
It works on Pytorch, and it's great. It talks about compute as a first principle. So here's what I mean by copying memory and compute. There might be a fair few things you're not familiar with here, but that's okay. But just be aware, bandwidth. So bandwidth costs are essentially the cost paid to move data from one place to another. That's what I was talking about, copying stuff from the CPU to the GPU. And then also there's one more, where is it? Overhead. Overhead is basically everything else. I call it overhead. There are different terms for different things. This article is excellent. So I'm going to just copy this in here, and you'll find this in the resources, by the way. So for more on how to make your models compute faster, see here. Lovely. So right now, our baseline model is performing the best in terms of results, and in terms of, or actually, our model computing on the GPU is performing faster than our CPU. Again, yours might be slightly different. For my case, for my particular hardware, CUDA is faster, except Model 0, our baseline, is better than Model 1. So what's to do next? Well, is to keep experimenting, of course. I'll see you in the next video. Welcome back. Now, before we move on to the next modeling experiment, let's get a results dictionary for our Model 1, our model that we trained on. So just like we've got one for Model 0, let's create one of these for Model 1 results, and we can create that with our model function. So go right back down to where we were. I'll just get rid of this cell, and let's type in here, get Model 1 results dictionary. This is helpful, so later on we can compare all of our modeling results because they'll all be in dictionary format. So we're going to Model 1 results equals of our model on our model equals Model 1, and we can pass in a data loader, which is going to be our test data loader. We're going to pass in a loss function, which is going to equal our loss function, and we can pass in our accuracy function equals accuracy. Wonderful. And then if we check out our Model 1 results, what do we get? Oh no, we get an error. Did we get the code right? That looks right to me. Oh, what does this say? Runtime error. Expected all tends to be on the same device. But found at least two devices, CUDA and CPU. Of course. So why did this happen? Well, let's go back up to our eval model function, wherever we defined that. Here we go. Ah, I see. So this is a little gotcha in Pytorch or in deep learning in general. There's a saying in the industry that deep learning models fail silently, and this is kind of one of those ones. It's because our data and our model are on different devices. So remember how I said the three big errors are shape mismatches with your data and your model, device mismatches, which is what we've got so far, and then data type mismatches, which is if your data is in the wrong data type to be computed on. So what we're going to have to do to fix this is, let's bring down our eval model function down to where we were, and just like we've done in our test step and train step functions, where we've created device agnostic data here, we've sent our data to the target device, we'll do that exact same thing in our eval model function. And this is just a note for going forward. It's always handy to, where you can, create device agnostic code. So we'll go down to eval model function here, for xy in our data loader, let's make our data device agnostic. So just like our model is device agnostic, we sent it to the target device, we will do the same here. X.toDevice and then Y.toDevice. Let's see if that works. We'll just rerun this cell up here. I'll grab this. We're just going to write the exact same code as what we did before, but now it should work because we've sent our... We could actually also just pass in the target device here. Device equals device. That way we can pass in whatever device we want to run it on. And we're going to just add in device here. Device equals device. That way we can pass in whatever device we want to run it on. And we're going to just add in device here. Device equals device. And let's see if this runs correctly. Beautiful. So if we compare this to our Model 0 results, it looks like our baseline's still out in front. But that's okay. We're going to, in the next video, start to step things up a notch and move on to convolutional neural networks. This is very exciting. And by the way, just remember, if your numbers here aren't exactly the same as mine, don't worry too much. If they're outlandishly different, just go back through your code and see if it's...
Not that. Let's go back. This eval model. It's not done right. device and manage syntax. Why do I often just enter a name instead of comma there? Anyhow, I've accuracy in English, so I guess it's fine. Let's just run that.
Maybe a cell hasn't been run correctly or something like that. If there are a few decimal places off, that's okay. That's due to the inherent randomness of machine learning.
Oh, I keep on running the test training and testing loop again and again. No, stop. Missing one. Okay. Device.
And deep learning. But with that being said, I'll see you in the next video. Let's get our hands on convolutional neural networks. Welcome back. In the last video, we saw that our second modeling experiment, Model 1, didn't quite beat our baseline. But now we're going to keep going with modeling experiments. We're going to move on to Model 2, and this is very exciting. We're going to build a convolutional neural network, which is also known as CNN. CNNs are also known as ConvNets, and CNNs are known for their capabilities to find
okay, so maybe that's what's
data.
needed for the visual.
What are we going to do? Well, let's jump back into the keynote. We had a look at this slide before. This is the typical architecture of a CNN. There's a fair bit going on here, but we're going to step through it one by one. We have an input layer, just like any other deep learning model. We have to input some kind of data. We have a bunch of hidden layers. In our case, in a convolutional neural network, you have convolutional layers. You often have hidden activations or nonlinear activation layers. You might have a Boolean layer. You generally always have an output layer of some sort, which is usually a linear layer. And so the values for each of these different layers will depend on the problem you're working on. So we're going to work towards building something like this. And you'll notice that a lot of the code is quite similar to the code that we've been writing before for other Pytorch models. And the only difference is in here is that we're going to use different layer types. And so if we want to visualize a CNN in a colored block edition, we're going to code this out in a minute, so don't worry too much. We have a simple CNN. You might have an input, which could be this image of my dad eating some pizza with 2 thumbs up. We're going to pre-process that input. We're going to, in other words, turn it into a tensor in red, green, and blue for an image. And then we're going to pass it through a combination of convolutional layers, ReLU layers, and pooling layers. Now again, this is a thing to note about deep learning models. I don't want you to get too bogged down in the order of how these layers go, because they can be combined in many different ways. In fact, research is coming out almost every day, every week, about how to best construct these layers. The overall principle is what's more important, is how do you get your inputs into an idealized output. That's the fun part. And then of course we have a linear output layer, which is going to output however many classes or value for however many classes that we have in the case of classification. And then if you want to make your CNN deeper, this is where the deep comes from deep learning, you can add more layers. So the theory behind this, or the practice behind this, is that the more layers you add to your deep learning model, the more chances it has to find patterns in the data. Now, how does it find these patterns? Well, each one of these layers here is going to perform, just like what we've seen before, a different combination of mathematical operations on whatever data we feed it. And each subsequent layer receives its input from the previous layer. In this case, there are some advanced networks that you'll probably come across later in your research and machine learning career that use inputs from layers that are kind of over here, all the way down here or something like that. They're known as residual connections. That's beyond the scope of what we're covering for now. We just want to build our first convolutional neural network. And so, let's go back to Google Chrome. I'm going to show you my favorite website to learn about convolutional neural networks. It is the CNN Explainer website. And this is going to be part of your extra curriculum for this video, is to spend 20 minutes clicking and going through this entire website. We're not going to do that together because I would like you to explore it yourself. That is the best way to learn. So what you'll notice up here.
Let's do that. Let's just send to it first.
And this is going to be our input. So let's start with pizza. And then we have a convolutional layer, a ReLU layer, a conv layer, a ReLU layer, max pool layer, conv2, ReLU2, conv2, ReLU2, max pool2. This architecture is a convolutional neural network and it's running live in the browser. And so we pass this image, you will notice that it breaks down into red, green, and blue. And then it goes through each of these layers and something happens. And then finally we have an output. And you notice that the output has 10 different classes here because we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different classes of image in this demo here. And of course we can change this. If we had 100 classes, we might change this to 100. But the pieces of the puzzle here would still stay quite the same. And you'll notice that the class pizza has the highest output value here because our images of pizza. If we change to, what is this one? Espresso. It's got the highest value there. So this is a pretty well-performing convolutional neural network. Then we have a sport car. Now, if we click on each one of these, something is going to happen. Let's find out. We have a convolutional layer. So we have an input of an image here that's 64 by 3. This is Color Channel's last format. So we have a kernel, and this kernel, this is what happens inside a convolutional layer. You might be going, well, there's a lot going on here, and yes, of course there is, if this is the first time you've ever seen this. But essentially what's happening is a kernel, which is also known as a filter, is going over our image pixel values, because of course they will be in the format of tensor, and trying to find small little intricate patterns in that data. So if we have a look at here, and this is why it's so valuable to go through this and just play around with it. We start in the top left corner, and then slowly move along. You'll see on the output on the right-hand side, we have another little square. And you notice in the middle all of those numbers changing? Well, that is the mathematical operation that's happening as a convolutional layer convolves over our input image. How cool is that? You might be able to see on the output there that there's some slight values for, like, look around the headlight here. Do you notice on the right how there's some activation? There's some red tiles there. Well, that just means that potentially this layer or this hidden unit, and I want you to zoom out for a second, because we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hidden units. Each one of these is going to learn a different feature about the data. And now the beauty of deep learning, but also one of the curses of deep learning, is that we don't actually control what each one of these learns. The magic of deep learning is that it figures it out itself what is best to learn. If we go into here, notice that each one we click on has a different representation on the right-hand side. And so this is what's going to happen layer by layer as it goes through the convolutional neural network. And so if you want to read about what is a convolutional neural network, you can go through here. But we're going to replicate this exact neural network here.
Let's run this. What's this? That's a ladybug. Let's do pizza because everyone loves pizza. Alright, if you don't like pizza, we can't be friends. Sorry. Anyhow, add a the numbers change with each pixel and then this through the convolution convert. Okay, let's just put this on to Google and see how we can pronounce this.
4 साल की मेहनत 700 से ज़्यादा टेस्ट फ्लाइट
Convolutional.
Okay, yeah, this goes through the relu layer after that, but why is the relu layer here almost equal to nothing? Oh, is it because let's just see all the number crunching that took place here resulted in negative numbers. Yeah, everything is negative, so therefore it changes to 0. Oh yeah, max of 0 and negative values here. That's why you got an empty image here. What about here though? Yeah, most of it is positive. And yeah, all of this got fed into our this thing, and what's happening here though? Oh, I see. So the image here is formed by this and the blue and the green channel. Jeez, just look at this. The amount of look at the closeness of those lines. There's just too much number, too much. Is too much a word? Anyhow, there's lots of number crunching taking place here, all to determine that this image over here is a pizza. What's this? What's this? Bell pepper? Yeah. We have a car here. This is an orange, right? Although, maybe I need to. What's the opposite of enlarge? Opposite of enlarge. Reduction, okay, but diminution. You learn something new every day. Anyway, let's just reduce the size here. Yeah, that's an orange, alright. Although it is a bit, it would be a bit confusing for the CNN, right? They whoever took the image drew a face on top of the orange. This is a red panda. We have koala here. Ah, okay. Huh. Let's go back.
With Pytorch code. That's how I prefer to learn it. But if you want the intuition behind it, the math behind it, you can check out all these resources here. That is your extra curriculum for this video. So we have an input layer, we have a convolutional layer. You can see how the input gets modified by some sort of mathematical operation, which is of course convolutional operation. We have there all different numbers, finding different patterns in data. This is a really good example here. You notice that the output size slightly changes. That'll be a trend throughout each layer. And then we can understand the different hyperparameters. But I'm going to leave this for you to explore on your own. In the next video, we're going to start to write Pytorch code to replicate everything that's going on here. So I'm going to link this in here to find out what's happening inside CNN. See this website. Yeah. So
I think, as promised, let me just turn off my fan here. Stretch a bit every now and then. I do remember reading an article which said sitting is the new smoking.
Join me
Don't
in the next
sit
video. This is
for
super exciting. We're going to build our first convolutional neural
don't
network
sit
for
for
computer vision.
long periods of time, or always get up from time to time.
I'll see you there. Welcome back. In the last video, we went briefly through the CNN Explainer website, which is my favorite resource for learning about convolutional neural networks. And of course, we could spend 20 minutes clicking through everything here to find out what's going on with a convolutional neural network. Or we could start to code one up. So how about we do that, hey? If in doubt, code it out. So we're going to create a convolutional
If it
neural
not
network. And what I'm going to do is we're going to build this model together in this video. And then because it's going to use layers or Pytorch layers that we haven't looked at before, we're going to spend the next couple of videos stepping through those layers. So just bear with me as we code this entire model together. We'll go break it down in subsequent videos. So let's build our first convolutional neural network. That's a mouthful, by the way. I'm just going to probably stick to saying CNN. Fashion MNIST. We're up to model v2. We're going to subclass nn.module, as we always do when we're building a Pytorch model. And in here, we're going to say model architecture that replicates the tiny VGG. And you might be thinking, where did you get that from, Daniel? Model from CNN Explainer website. And so oftentimes when convolutional neural networks or new types of architecture come out, the authors of the research paper that present the model get to name the model. And so that way in the future, you can refer to different types of model architectures with just a simple name like tiny VGG, and people kind of know what's going on. So I believe somewhere on here it's called tiny VGG. Tiny VGG. We have nothing. Yeah, there we go. In tiny VGG. Do we have more than one tiny? Tiny, yeah, tiny VGG. And if we look up VGG, ConvNet, VGG16 was one of the original ones. VGG, very deep convolutional neural networks, VGGNet. There's also ResNet, which is another convolutional neural network. You can also, I don't want to give you my location, Google. You can go popular CNN architectures. And this will give you a fair few options. LaNet is one of the first, AlexNet, ZFNet, whole bunch of different resources. And also, how could you find out more about a convolutional neural network? What is a convolutional neural network? You can go through that. But let's stop that for a moment. Let's code this one up together. So we're going to initialize our class here, defInit. We're going to pass it in an input shape, just like we often do. We're going to put in a number of hidden units, which is an int. And we're going to put in an output shape, which is an int. Wonderful. So nothing too outlandish that we haven't seen before there. And we're going to go super.init to initialize our initializer, for lack of a better way of putting it. Now, we're going to create our neural network in a couple of blocks this time. And you might often hear when you learn more about convolutional neural networks, or I'll just tell you that things are often referred to as convolutional blocks. So if we go back to our keynote, this combination of layers might be referred to as a convolutional block. And a convolutional block, a deeper CNN, might be comprised of multiple convolutional blocks. So to add to the confusion, a block is comprised of multiple layers, and then an overall architecture is comprised of multiple blocks. And so the deeper and deeper your models get, the more blocks it might be comprised of, and the more layers those blocks may be comprised of within them.
Oh, haha, we have Actionian back on our stream. Hey, hello there. How are you?
So it's kind of like Lego, which is very fun. So let's put
Haha, there you go. Yeah, sure. Hit me with it.
together an NN sequential.
By the way, your voice is very bad in the stream. Oh, it might be with I think I have a cold or something. Let's see. See what I can do. It should be the same, really. It's my not called. Oh, it's Echo. Oh, all right. Huh. I'm just gonna test here and shrill. Hello. Hmm. It sounds fine to me. Maybe it's something from your side, perhaps. Uh, it's the exact same configuration I had yesterday. I did put my fan. Yeah, I did put my fan a bit before, and that is a little things being. Anyway, I don't see that on the. By the way, on CNN, they are on good for images. CNNs are only good for images, huh? We need to use transformers for other type of visual data. Because CNNs have an implicit bias that limits their ability. Implicit bias means we can't control the bias that's put in there, right?
Now, the first few layers here that we're going to create in conv block 1 are nn.conv2d. Oh, look at that. Us running us.
Guess the bias. Uh, Is it implicit bias arises out of the architecture? Hmm. Wait a second, let me just continue my monitor here. Okay, that should be good enough. I might have lost your messages by the way. The implicit bias arises out of the architecture. Hmm. I always like it when I have to go ahead and search things up. Implicit bias and deep learning. Hmm. That's some research paper here. Okay, it's an unco. Oh no, that's not related to deep learning. CNNs have regional scanners that extract. We have a lot of bots coming in and anyway. What's that? CNN have regional scanners that extract features that limits them from building long context relations. Second and final. Oh, basically they can find long patterns, is what you're saying, right? From the last example. Hmm. What is regional scanner though? Oh, you mean let me just show you this. It was shown on the video. I already forgot the. Let's see an explainer. Is this what you mean by regional? Like it scans each pixel, and in this case, since everything is negative, once the layer is applied, the image here is just you know gone, like empty. It looks at a region at a time, yeah. But transform based models can do more because they require much more data to converge. Yeah. Basically, you're saying is that CNN looks at everything from one pixel at a time, whereas if it was a video or something where it would use a transformer, there would be more to it, like audio and video, timestamp, more data. Yeah, nearby pixel is given more importance. Oh, it limits the region, is what you're saying. So when we use a scene, it might like the region that it scans like would be tiny, whereas a transformer, yeah, okay, transformer would attend to like the entire image at the same time. Huh? Okay, there we go. It's always fun when I figure things out. Yeah. All right. Jeez, I need to check myself out. Yeah, they need a lot more data.
Our first CNN layer,
That
and
makes
we have to
sense.
define something here which is in channels. So this channels refers to the number of channels in your visual data, and we're going to put in input shape. So we're defining the input shape. This is going to be the first layer in our model. The input shape is going to be what we define when we
Yep. Let's now build this CNN anyways. We have a input shape. If you don't mind sharing with me, are you a student or like a working professional? I really think you are a machine learning engineer, like behind sitting behind the screen right now. I mean, come on. You might be kidding with me that you seem to know quite a lot on this area. Alright, so yeah, we are creating a block here, and then maybe we'll create the we'll stack multiple blocks together.
Instantiate this class. And then the out channels. Oh, what's the out channels going to be? Well, it's going to be hidden units, just like we've done with our previous models. Now, the difference here is that in NNConv2D, we have a number of different hyperparameters that we can set. I'm going to set some pretty quickly here, but then we're going to step back through them, not only in this video, but in subsequent videos. Oh, we've got a fair bit going on here. We've got in channels, which is our input shape. We've got out channels, which are our hidden units. We've got a kernel size, which equals 3, or this could be a tuple as well, 3 by 3, but I just like to keep it as 3. We've got a stride, and we've got padding. Now, because these are values we can set ourselves, what are they referred to as? Let's write this down. Values we can set ourselves in our neural networks, in our NN's neural networks.
There is a video where this guy has with what is chip Shukan? Did you do a typo there?
Called hyperparameters. So these are the hyperparameters of NNConv2D. And you might be thinking, what is 2D for? Well, because we're working with two-dimensional data, our images have height and width. There's also conv1D for one-dimensional data, 3D for three-dimensional data. We're going to stick with 2D for now.
Okay, all right. So we can build a model with an actual 3D models. Why did I do that? When you realize all of this is 5% of actual work needed. Models are a very tiny part of the actual solution. What is the rest 95% then? Is it like gathering data and then converting them into tensors? Data aggregation, right? Deploying and monitoring. I guess I can't say I haven't deployed I've deployed a model only to Hugging Face, and that's through the inference endpoint. I guess, yeah, you might be right. It'll take a very, very long time to monitor, go back, improve. It's a loop. This part is solved. It's mostly plug and play in real life. Yeah, I would imagine so. There would be plenty of things out there. No one plays with architecture. They just copy it, huh? I guess I mean, in a way that's what they should do, because this is lots of research has been spent to create this, right? Like tests and everything, so but they just use that. Yeah, it's super duper researchy. I would imagine so, yeah.
And so what do each of these hyperparameters do? Well, before we go through what each...
The kernel size, is kernel size the, was it looking into 3 per pixels side by side? I think that's what you meant. I think you mentioned it in one of your
One of them do. We're going to do that when we step by step through this particular layer. What we've just done is we've replicated this particular layer.
Yeah, of course. I mean, it is with everything code, right? Like we just see the if we just see the final output, we'll just get overwhelmed with all the math and everything involved, and that would just demotivate people from learning. Not just machine learning. You can just put that scenario for anything.
Yeah, of the CNN Explainer website. We've still got...
Is my audio clear, by the way, or?
We've still got another conv and a relu and a max pool and a conv and a relu and a conv and a relu and a max pool. But this is the block I was talking about. This is one block here of this neural network, or at least that's how I wrote it down.
Good.
And this is another block. You might notice that they're comprised of the same layers, just stacked on top of each other. And then we're going to have an output layer. And if you want to learn about where the hyperparameters came from, what we just coded,
must be my call.
Well, one, you could go...
Not a call. I don't know what's happening today.
Pytorch documentation, Pytorch NNConv2D.
But we'll still continue on our
There's the mathematical
progress
that we
here.
talked about
Can't let that fail.
Touched on, stepped on. Is the right word? So create a conv layer. It's there. But also this is why I showed you this beautiful website, so that you can read about these hyperparameters down here. Understanding hyperparameters. So your extra curriculum for this video is to go through...
You know what, let's do that first. Right, hold on a second. color size, as imagine it creates a square, 2 by 2 square here. So it looks at 3 pixels at a time here, 4 pixels at a time here. Okay, that's what color size does. What about padding? Wait. Before we look at padding, let's just, yeah, okay, input size is just how many pixels there are, right? 7 times 7, 49. What is stride? Stride apparently decreases. Hmm. Oh, I see it. This whole thing is now treated as one. Maybe that's what it's trying to show. Stride is how much it skips by when it takes a step. So we have stride as 2 here. Oh, I see. It's skipping 2 blocks here. So if I put that to 3, it's not working because it can't finish with 3. So maybe if we what if we yeah, if we decrease that to 6? Okay, thank you Action, yeah, for that. And what is padding? Why would you wanna do that though? Like, is this creating artificial data, like how you mentioned? It's like range function of Python. Oh, you mean stride or padding? I think you meant padding here. No, wait. Yeah, stride. Yeah, it's the third. Yeah, that's right. Hmm. All right. Let's go back. I did not understand what padding is though. Do you happen to know? It's just. Maybe let's just. Let me just see. If I increase the padding, it just. Yeah, it creates. Okay. I understood, but why would it do this? Why padding and padding is using zero? Keeps the input size consistent during convolution, preventing data loss at the edges or because of strides or something. Okay, cool. Yeah, I think yeah, it's put borders. Yeah, I understood that. I want to know why do they do that though. Anyhow,
Through this little
let's
graphic
go
here
through the
and
video
see if you can
now.
find out what padding means, what the kernel size means, and what the stride means. I'm not going to read through this for you. You can have a look.
Oh, because we need to put it on GPU. Yeah, to avoid shape issues, right? To avoid size issues.
Look at this interactive plot. We're going to keep coding because that's what we're all about here. If in doubt, code it out. So
Yeah.
we're going to now add a ReLU layer. And then after that, we're going to add another conv2d layer. And the in channels here is going to be the hidden units because we're going to take the output size of this layer and use it as the input size to this layer. We're going to keep going here. Out channels equals hidden units again in this case. And then the kernel size is going to be.
Yeah, of course. Now, what system do you have? Like, what's your daily driver that you use? Is it a laptop or a CPU, or what do you use? Oh, you use Mac? All right. Um, is it okay to say that when running like you know machine learning, Windows would be better, or what do you think? Or maybe the answers to it is Linux, although Nvidia has a thing with Linux, right? So it is Windows. Is that what you agreed with me?
3 as well. Stride will be 1. Padding will be 1. Now, of course, we can change all of these values later on, but just bear with me while we set them how they are.
Yeah.
We'll have another ReLU layer.
Oh, Linux plus NVIDIA is the best to use, okay, but Windows is easier to use. I guess, yeah, Windows is definitely easy to use. I guess, is it like safe to say that in terms of AI, like for AI purposes, not for gaming purposes, for AI purposes, NVIDIA is better than AMD? I guess I'm generalizing it too much, ain't I? Alright, that's good to know.
And then we're going to finish off with the NN Max Pool 2D layer. Again, the 2D comes
Yes,
from the same reason we use
definitely. What's
Compiler
that?
for working with 2D behavior.
10,000%.
I'm going to set the kernel size here to be equal to 2.
It's max pool 2D now. Is that some other layer?
And of course, this can be a tuple as well, so it can be 2, 2. Now, where could you find out about NN Max Pool 2D? Well, we go NN
Check
Max
the
Pool
docs,
2D.
of
What
course.
does this do? Applies a 2D max pooling over an input signal composed of several input planes. So it's taking the max of an input. And we've got some parameters here.
Yeah, of course. I guess NVIDIA took advantage of the AI boom, and although I guess why doesn't the AMD do it? You know?
Size. The size of the window to take the max over. Now, where have we seen a
Yeah, they created the AI boom. Oh yeah, they made CUDA, of course. Yeah, and CUDA is more efficient for AI purposes. So yeah, I guess
window before? I'm just going to close these.
they made a technology. Yeah.
We come back up. Where do we see a window? Let's dive. The size of the window to take the max over. Now, where have we seen a window before? I'm just going to close these.
Do people even use Intel GPUs, or I mean, I know Intel like has GPUs, but it's easier to use, not efficient, much easier to use, much easier. I would imagine so because of all the drivers and everything that's needed.
We come back up.
Like it would be a hassle to go about, and I would imagine so. Anyway.
Where do we see a window? Let's dive into the max pool layer. See where my mouse is? Do you see that 2 by 2? Well, that's a window. Now look at the difference between the input and the output. What's happening? Well, we have a tile that's 2 by 2, a window of 4, and the max, we're taking the max of that tile. In this case, it's 0. Let's find the actual value. There we go. So if you look at those 4 numbers in the middle, inside the max brackets, we have 0.07, 0.09, 0.06, 0.05, and the max of all those is 0.09. And you'll notice that the input and the output shapes are different. The output is half the size of the input. So that's what max pooling does. It tries to take the max value of whatever its input is and then outputs it on the right here. And so as our data, this is a trend in all of deep learning actually, as our image moves through, this is what you'll notice. Notice all the different shapes here. Even if you don't completely understand what's going on here, you'll notice that the 2 values here on the left start to get smaller and smaller as they go through the model. And what our model is...
it gets more blurry in a sense that, what's that? The CUDA driver better design, and they have insane cache and they can be caught up. People can try and fail their way. I mean, I guess in the long run that's a bad thing, because whenever there is not any competition, then there is no innovation. They won't be they would be less reluctant to innovate. They'll become they'll become less reluctant. Yeah, monopoly is bad. We need competition for innovation in this world. Anyways.
Trying to do here is take the input and learn a compressed representation through each of these layers. So it's going to smush and smush and smush, trying to find the most generalizable patterns to...
PC building is one of those things where I did not have any knowledge, and I had to learn it all very recently, in fact. They innovated into the space and keep innovating better than anybody for now. But if they remain as a monopoly for long, then they won't care about innovation. They're not rent seekers.
Get to the
I
ideal
didn't
outputs.
understand what you
And that
meant
input
by
is actually
that.
going to be a feature vector to our final layer. So a lot going on there, but let's keep coding. What we've just completed is this first block. We've got a conv layer, a ReLU layer, a conv layer, a ReLU layer, and a max pool layer. Look at that. Conv layer, ReLU layer, conv layer, ReLU layer, max pool. Should we move on to the next block? We can do this one a bit faster now because we've already coded the first one.
NVIDIA does that. I know I don't know how reliable this source is, but I think it was from one short or something. Nvidia makes a 3000% profit on their AI specific CPU on there. Yeah, yeah. I think in the short they said 30x, but yeah, they're literally printing money at this point.
So I'm going to do NN
And
sequential as well.
companies buy
And
it
then we're going
because
to go
there
NN.
isn't any other reliable option available, right? At least for now.
.com 2D. We're going to set the in channels. What should the in channels be here? Well, we're going to set it to hidden units as well because our network is going to flow just straight through all of these layers.
They
And
need
the
to
output side of this
choke
is going to
up
be hidden units. And
on
so
as the workload is shifting from CPU to GPU. Oh, you mean companies, right?
we
Yeah,
want
they
the in
need
channels
to
to match
choke
up with
up
the
for
previous
sure.
layers out channels. So then we're going to go out channels.
I don't know, but I think the AI boom happened mainly due to GPT. Would you agree with me in saying that? At least that's how the common person came to know about AI and everything. AI was long there before that with Tesla and everything. Oh, 100% no? Alright. Okay. When do you think then the AI became well known to people? Before, I think I mentioned this to you yesterday maybe. Before, what's it? Yet to come. Okay. Um, hmm. Anyway, before OpenAI and everything, right? If you had asked me, like, what's a company which uses AI, the first thing that would go to my mind would be Tesla because of their, what's it, their cars and everything. Automatic cars. The entire UI will change. Entire UI for what? You mean GPT? By the way, are there any, I have heard that people at, like Reliance and IITs and everything like join together to create a language model for all the Indian languages for all soft. Oh wait, what was that? All days we had terminal UI, then we had GUI. Now we had LLM based UI. Ah, it will be literally like hmm. How long do you think that would take for that thing like to become you will talk to for yeah exactly 5 years, huh? Hmm. I agree with you. I mean, with the pace that AI is going, it is becoming good day by day.
Equals hidden units as well. We're going to set the kernel size. Kernel size equals 3. Stride equals 1. Padding equals 1. Then what comes next? Well,
ChatGPT was the first more art to come. Yeah. Are there any models which uh, I know the government or someone is trying to do that for Indian languages?
because the two blocks are
On top
identical,
of that,
com
or
block 1 and
yet,
com 2,
or
we can just go the exact same combination of layers. NN relu, NN com 2D, in channels equals hidden units, out channels equals, you might already know this, hidden units.
the Ola guy is a fraud. Hmm. I'm sorry, what is Ola doing exactly? Is it hmm, Ola? Maybe I'm not top of the latest news yet, but what's the thing with Ola? Is it the Google API thing or Maps API thing or he's leading the effort for the yeah. All right, Pytorch AI. Hmm. Hmm. Oh, that's what it's called. Pytorch AI. Why? Why do you think so? I mean, I don't know the reason. That's why I'm asking. We need researchers, not marketers. Huh. Well, I don't know anything about all that to comment on that, but yeah, I do agree we need researchers there. But I think there's equally we need like we need CEOs and everything, right? You can read papers. Hmm. I have to check on it. That's interesting, you know. I just heard like the baseline stuff about Indian language models.
Then we have kernel size equals 3. Oh, 32, don't want it that big. Stride equals 1. Padding equals
Oh, I see. Hmm. Gotcha. What you're trying to say is that all the AI research and everything, all the papers being released are not from like Indian universities and research places and stuff, right?
1. What comes next? Well, we have another ReLU layer.
I guess again it's a sad thing. Most of the universities out there they don't again this is another stat. Most of the engineering graduates out from India are not employable, which is it's a sad thing, you know. We need to improve that. Yeah, professors are bureaucratic in India. Very sad. Yeah, one of my far thing into the future is to and this is long term, very long term. Maybe when I become old and stuff, I really wanna change the education system in whatever way I can. Maybe not in a large scale, but you know, I can. I mean, I'll do it in small steps. Maybe you know, yeah, teach coding. That's what I was about to say. It's a life skill for sure. It's gonna become a yeah,
And
life
then what
skill
comes after that?
itself.
We have another max pool. And then max pool 2D, kernel size equals 2. Beautiful. Now, what have we coded up so far? We've got this. And then max pool 2D, kernel size equals 2. Beautiful. Now, what have we coded up so far?
You,
We've got this block, number 1. That's what this one on the inside here.
it's like no English. Yeah, I agree. I agree. Yeah, same here. Same here.
Kernel size equals 2. Beautiful. Now, what
Off tangent here. Do you play any games?
comes after that?
So
We have another max pool. And then max pool 2D, kernel size equals 2. Beautiful. Now, what
I spell this wrong. Probably missed some comma or something like that.
have we coded up so far? Max pool.
Let me turn on the that should be better. What's that? No games. I trek though and go on bike rides and hang on pets. Alright, go on bike rides and stuff. The area you're living is that like in the mountain region and stuff like or yeah in My we have pieces and stuff.
And then max ball 2D, kernel size equals 2.
Oh, what's that? It's abiogeographic. That's a new word for me. What is abiogeo? Abio? Or how do you pronounce that? Geographic. Biogeographic, okay. The study of geographic. Okay, I don't want to know what that is. It's a study of. Ah, okay. It's evergreen, alpine, and cold desert. Ah, okay, okay, gotcha. Anyway, you just told me what it is. The rest says evergreen. The first at 50 kilometers, it's called desert.
Ooh, beautiful. Now, what have we coded up so far? We've got this block, number 1. That's what this one on the inside here. And then we have com2, relu2, com2, relu2, max ball 2. So we built these 2 blocks. Now, what do we need to do? Well, we need an output
That's
layer.
cool.
And so, what did we do before when we made model 1? We built these 2 blocks. Now, what do we need to do? Well, we need an output layer. And so, what did we do before when we made model 1?
Alright, so coming back to the coding part, we made 2 blocks here with these many layers.
We flattened the inputs of the final layer before we put them to the last linear layer. So flatten. So this is going to be the same kind of setup as our classifier layer. Now, I say that on purpose because that's what you'll generally hear the last output layer in a classification model called, is a classifier layer. So we're going to have, these 2 layers are going to be feature extractors. In other words, they're trying to learn the patterns that best represent our data. And this final layer is going to take those features and classify them into our target classes.
I don't know, what is that?
Thinks best suits those
Educate
features, whatever our model
me,
thinks
yeah.
those features that it learned represents in terms of our classes. So let's code it out. We'll go down here. Let's build our classifier layer. This is our biggest neural network yet. You should be very proud. We have nn.sequential again. We're going to pass in nn.flatten because the output of these 2 blocks is going to be a multidimensional tensor, something similar to this size, 13, 13, 10. Because the output of these 2 blocks is going to be a multidimensional tensor, something similar to this size, 13, 13, 10. So we want to flatten the outputs into a single feature vector, and then we want to pass that feature vector to an nn.linear layer. And we're going to go in features equals hidden units.
We'll flatten it first. What's that? Place where life restarted after the great flood is where I live in, according to all books. Ah. I didn't know that. Malsya avatar of Vishnu wants the first man. That's cool. My new temple is 200 meters away from me.
Times something times something. Now, the reason I do this is because we're going to find something out later on with times 0, just so it doesn't error. But sometimes calculating what your in features needs to be is quite tricky. And I'm going to show you a trick that I use later on to figure it out. And then we have out features, relates to our output shape, which will be the length of how many classes we have, right? One value for each class that we have. And so, with that being said, let's now that we've defined...
Finally multiplied by 0 must be a typo, right?
will be the length of how many classes we have, right? One value for each class that we have. And so, with that being said, let's now that we've defined all of the components of our tiny VGG architecture, there's a lot going on, but this is the same methodology we've been using the whole time, defining some components and then putting them together to compute in some way in a forward method. So forward self x. How are we going to do this? We're going to set x is equal to self conv block 1 x. So x is going to go through conv block 1. It's going to go through the conv2d layer, relu layer, conv2d layer, relu layer, max pool layer, which will be the equivalent of an image going through this layer, this layer, this layer, this layer, this layer, and then ending up here. So we'll set it to that, and then we can print out x.shape to get its shape. We'll check this later on. Then we pass x through conv block 2, which is just going to go through all of the layers in this block, which is equivalent to the output of this layer, going through all of these layers. And then because we've constructed a classifier layer, we're going to take the output of this block, which is going to be here, and we're going to pass it through our output layer, or what we've termed it, our classifier layer. I'll just print out x.shape here, so we can track the shape as our model moves through the architecture. X equals self.classifier, x. And then we're going to return x. Woohoo! Look at us go. We just built our first convolutional neural network by replicating what's on a
Finally, feed that to classifier to flatten it out and then get it into our required shape.
Woohoo! Look at us go. We just built our first convolutional neural network by replicating what's on a CNN Explainer website. Now, that is actually very common practice in machine learning, is to find some sort of architecture that someone has found to work on some sort of problem and replicate it with code and see if it works on your own problem. You'll see this quite often. And so now let's instantiate a model. We'll go torch.manual C. We're going to instantiate our first convolutional neural network. Model 2 equals fashion mnist. We will go model v2, and we are going to set the input shape. Now, what will the input shape be? Well, I'll come 2D layer up here. The input shape is the number of channels in our images. So do we have an image ready to go? Image shape. This is the number of color channels in our image. We have 1. If we had color images, we would set the input shape to 3. So the difference between our convolutional neural network, our CNN, tiny VGG, and the CNN Explainer, tiny VGG, is that they are using color images. So their input is 3 here. So 1 for each color channel, red, green, blue. Whereas we have black and white images, so we have only one color channel, so we set the input shape to 1. And then we're going to go hidden units equals 10, which is exactly the same as what TinyVGG has used. 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that sets the hidden units value of each of our layers. That's the power of creating an initializer with hidden units. And then finally, our output shape is going to be what? We've seen this before. This is going to be the length of our class names, one value for each class in our dataset. And of course, we're going to send this model to the device. We're going to hit shift and enter. Oh no, what did we get wrong? Out channels, output shape. Where did I spell wrong? Out. We're going to hit shift and enter. Oh no, what did we get wrong?
Probably made some typo.
Out channels, output shape. Where did I spell wrong? Out channels, out channels, out channels. I forgot an L. Of course, typo.
Okay, let's just run this. What's the class name? Fashion feminist. Oh, okay, we did not write model there. Let's do that. Lowercase.
One value, create 2, 3, put shape to 1, 3 here. So 1 for each color channel, red, green, and blue. Whereas we have black and white.
Kernel size, kernel size, kernel size. Has a kernel size. This one also has a kernel size. Where's the error coming from? Oh, max poll 2D, okay. Kernel size. Ah, okay, there we go. What did we give
That's
kernel
instantiate sort of problem.
size
Look at us go. Architecture to through output layer. Is layer 2 layer, which will be the equivalent
two
of an image
itself?
going through on block 1. It's going to go through the com
for the first? Yeah, it's
2D layer,
two.
relu layer, com 2D layer, relu layer, max pool layer, which will be the equivalent of an image going through this layer, this layer, this layer, this layer, this layer, and then ending up here. So we'll set it to that, and then we can print out x.shape to get its shape. We'll check this later on. Then we pass x through com block 2, which is just going to go through all of the layers in this block, which is equivalent to the output of this layer going through all of these layers. And then because we've constructed a classifier layer, we're going to take the output of this block, which is going to be here, and we're going to pass it through our output layer, or what we've termed it, our classifier layer.
Now what? Gonna inspect the in channel. That should fix that, hopefully. Got a lot of typos in here. Alright,
Just print
perfect.
out x.shape here. So, now, that is actually very common practice in machine learning, is to find some sort of architecture that someone has. So now let's instantiate a model. We'll go torch.manual.c. We're going to instantiate our first convolutional neural network. Model 2. They are using color images, so their input is 1, 5, 6, 7, and then finally our output shape is. We're going to hit channels, out channels. I've forgotten L. Up size, kernel size. Where did we spell this wrong? Oh, here. Kernel size, and not. Oh, so we've got the video, but pat yourself on the back. We've written a fair bit of code here. This is a convolutional neural network that replicates the tiny VGG architecture on the CNN Explainer website. Now, don't forget, your extra curriculum is to go through this website for at least 20 minutes and read about what's happening in our models. We're focused on code here, but this is particularly where you want to pay attention to. If you read through this, understanding hyperparameters and play around with this, the next couple of videos will make a lot more sense. So read about padding, read about kernel size, and read about stride. I'll see you in the next video. We're going to go through our network step by step. Welcome back. Now, I'm super stoked because in the last video, we coded together our first ever convolutional neural network in Pytorch. So, well done. We replicated the tiny VGG architecture from the CNN Explainer website, my favorite place for learning about CNNs in the browser. So now, we introduced two new layers that we haven't seen before, conv2d and maxpool2d. But they all have the same sort of premise of what we've been doing so far, is that they're trying to learn the best features to represent our data in some way, shape, or form. Now, in the case of maxpool2d, it doesn't actually have any learnable parameters. It just takes the max, but we're going to step through that later on. Let's use this video to step through nnconv2d. We're going to do that with code. So we'll make a new heading here. 7.1, stepping through nnconv2d. Beautiful. Now, where could we find out what's going on in nnconv2d? Well, of course, we have the documentation, nnconv2d. We've got Pytorch. So if you want to learn the mathematical operation that's happening, we have this value here, this operation here. Essentially, it's saying the output is equal to the bias term times something plus the sum of the weight times something times the input. So do you see how just the weight matrix, the weight tensor, and the bias value manipulating our input in some way equals the output? Now, if we map this, we've got batch size, channels in, height, width, channels out, etc., etc. But we're not going to focus too much on this. If you'd like to read more into that, you can. Let's try it with code. And we're going to reproduce this particular layer here, the first layer of the CNN Explainer website, and we're going to do it with a dummy input. In fact, that's one of my favorite ways to test things. So I'm just going to link here the documentation. See the documentation for nnconv2d here. And if you'd like to read through more of this, of course, this is a beautiful place to learn about what's going on. There's the shape, how to calculate the shape, height out, width out, etc. That's very helpful if you need to calculate input and output shapes. But I'll show you my trick for doing so later on. We have here, let's create some dummy data. So I'm going to set torch manual C. We need it to be the same size as our CNN Explainer data. So 64, 64, 3, but we're going to do it Pytorch style. This is color channels last. We're going to do color channels first. So how about we create a batch of images? We're going to be writing torch.randn, and we're going to pass in size equals 32, 3, 64, 64. And then we're going to create a singular image by taking the first of that, so image is 0. Now let's get the image batch shape, because a lot of machine learning, as I've said before, and deep learning is making sure your data has the right shape. So let's check images.shape, and let's check single image shape. We're going to go test image.shape, and finally, we're going to print, what does the test image look like? We'll get this on a new line, hey? New line, test image. This is, of course, not going to be an actual image. It's just going to be a collection of random numbers. And, of course, that is what our model is currently comprised.
Yep, we're just doing that to know the shape, right?
Of. Model 2, if we have a look at what's on the insides, we are going to see a whole bunch of random numbers. Look at all this. What do we have? We scroll up. It's going to give us a name for something. We have conv block 22. We have a weight. We have a bias. Keep going up. We go right to the top. We have another weight. Keep going down. We have a bias, a weight, etc., etc. Now, our model is comprised of random numbers, and what we are trying to do is, just like all of our other models, is pass data in and adjust the random numbers within these layers to best represent our data. So let's see what happens if we pass some random data through one of our conv2d layers. So let's go here. We're going to create a single conv2d layer. Now, it's the random, etc., etc. Conv block 2 numbers. Data has. Now, let's get the image batch shape, because a lot of machine learning, as I've said before, and deep learning is making sure your data has the right shape. So let's check images.shape, and let's check single image shape. We're going to go test image.shape, and finally, we're going to print, what does the test image look like? We'll get this on a new line, hey? New line, test image. This is, of course, not going to be an actual image. It's just going to be a collection of random numbers. And, of course, that is what our model is currently comprised of. Model 2, if we have a look at what's on the insides, we are going to see a whole bunch of random numbers. Look at all this. What do we have? We scroll up. It's going to give us a name for something. We have conv block 22. We have a weight. We have a bias. Keep going up. We go right to the top. We have another weight. Keep going down. We have a bias, a weight, etc., etc. Now, our model is comprised of random numbers, and what we are trying to do is, just like all of our other models, is pass data in and adjust the random numbers within these layers to best represent our data. So let's see what happens if we pass some random data through one of our conv2d layers. So let's go here. We're going to create a single conv2d layer. So conv layer equals, what does it equal? And then conv2d, we're going to set the in channels is equal to what? Oh, revealed the answer too quickly. 3. Why is it 3? Well, it's because because the in channels is the same number of color channels as our images. So if we have a look at our test image shape.
What languages do you code and what tech stack do you use or are familiar with? Right now, I'm very much proficient in Python. I do know JavaScript too, enough JavaScript to survive, although I haven't coded any, anything in Node.js yet. But I do know JavaScript enough. And that's it for languages. And somewhere along the lines, I did learn Java, but I've completely forgotten that and forgot that. Okay, anyway, tech stack. Um, what tech stack do I use? So I use in Python. What I mainly do is web scraping and automations. With Selenium and stuff. So yeah, yeah. I guess that's what I guess that I hope that answers your question. In terms of making websites and stuff, I have used Flask and everything. In short, if it is anything to do with Python, I could probably do it. Can you do me a favor? What is it? Go ahead.
What do we have? 3. It has 3 color channels. That is the same as the value here, except the order is reversed. This is color channels last. Pytorch defaults to color channels first. So, or for now it does. In the future, this may change. So
That's a very big. What's it? Can you build a project that looks into all your skills into a beautiful project which you can see? Are you saying streamer project basically? Is that what you're saying?
just keep that in mind. So out channels equals 10. This is equivalent to the number of hidden units we have. I don't want that one just yet. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have that 10 there. So we have 10 there. Then we have kernel size. Oh, what is
Yeah, basically, I'm asking you, do you mean basically take all the skills that I'm proficient in and build a project based off it? Is that what you mean? I mean, stream a project while building it. Is it better now? So, what I'm asking is, yeah, okay. All right, cool. I mean, that is in alignment with my plan. So, my plan here at Shinyam is to once I finish the course and I'm proficient in the sense or I have enough skill to get started with the project. I'll create my own project with the yeah, exactly, with machine learning and stuff. That's my plan. Yeah.
the kernel?
You'll be interested in seeing that?
Well, it's not KFC, I can tell you that. And then we have Stride.
All right, I appreciate the enthusiasm. For sure, I'll surely do that. It is anyway in alignment with my plans. Although I need to finish all of this first, and that would take some time on it. For sure, let's come to that point. Make it as complete as possible. Of course, will do.
And then we have padding. We're going to step through these in a second. But let's check out the kernel. And this kernel can also be 3 by 3, but it's a shortcut to just type in 3. So that's what it actually means if you just type in a single number. It's equivalent to typing in a tuple. Now, of course, you could find that out by reading through the documentation here. But where did I get that value? Well, let's dive into this beautiful website and let's see what's happening. So we have a kernel here, which is also called a filter. So the thing I'm talking about is this little square here, this kernel. Oh, we can see the weights there at the top. This is how beautiful this website is. So if we go over there, this is what's going to happen. This is a convolution. It starts with this little square, and it moves pixel by pixel across our image, and you'll notice that the output is creating some sort of number there, and you'll notice in the middle we have a mathematical operation. This operation here is what's happening here. Right, weight times the input. That's what we've got there. Now, the beauty of Pytorch is it does all of this behind the scenes for us. So again, if you'd like to dig more into the mathematical operation behind the scenes, you've got the resource here, and you've also got plenty of other resources online. We're going to focus on code for now. So if we keep doing this across our entire image, we get this output over here. So that's the kernel. Now, where did I get 3 by 3 from? Well, look at this. 1, 2, 3, 1, 2, 3, 1, 2, 3. 3 by 3, we have 9 squares. Now, if we scroll down, this was your extra curriculum for the last video. Understanding hyperparameters. What happens if we change the kernel size to 3 by 3? Have a look at the red square on the left. Now, if we change it to 2 by 2, it changed again. 3 by 3, this is our kernel, also known as a filter, passing across our image, performing some sort of mathematical operation. And now the whole idea of a convolution layer is to try and make sure that this kernel performs the right operation to get the right output over here. Now, what do these kernels learn? Well, that is entirely up to the model. That's the beauty of deep learning, is that it learns how to best represent our data, hopefully, on its own, by looking at more data. And then so if we jump back in here, so that's the equivalent of setting kernel size 3 by 3. What if we set the stride equal to 1? Have we got this in the right order? It doesn't really matter. Let's go through stride next. If we go to here, what does stride say? Stride of the convolution, of the convolving kernel. The default is 1. Wonderful. Now, if we set the stride, or if we keep it at 1, it's a default 1, it's going to hop over, watch the red square on the left, it's going to hop over 1 pixel at a time. So the convolution, the convolving, happens 1 pixel at a time. That's what the stride sets. Now, watch what happens when I change the stride value to the output shape. Wow. Do you notice that it went down? So we have here, the kernel size is still the same, but now we're jumping over 2 pixels at a time. Notice how on the left, 2 pixels become available, and then if I jump over again, 2 pixels. So the reason why the output compresses is because we're skipping some pixels as we go across the image. And now this pattern happens throughout the entire network. That's one of the reasons why you see the size of our input,
Random
the size
thing.
of each
You
layer.
want to have your brain try APL. I tried and just gave up after 3 days. What is APL? Oh, is that a language of some sort? APL. Programming language. But I heard that name before. Whoa, what is this? My god, how do you even code in that? That's crazy. Yeah, exactly. Why? Uh, and people I look up to swear by it. You know, one of the things I want to do later alongside this is, stream DSA too.
Down over time.
Data
What our convolutional
structures
layer is doing, in
and
fact, a lot
algorithms and stuff.
of deep learning neural networks do is they try to compress the input into some representation that best suits the data. Because it would be no point of just memorizing the exact patterns. You want to compress it in some way. Otherwise, you just might as well move your input data around. You want to learn generalizable patterns that you can move around. And so we keep going. We've got padding equals 0. Let's see what happens here. If we change the padding value, what happens? Up, down. Notice the size here.
What's that? Pure researchers. Nah, please no. Please know what? Sorry. It gives little utility to people, and there are a lot of people during DSA. Oh, data structures and algorithms. But I mean, it's for my benefit. Like, I don't know that much about DSA stream as I run through it. Today is a bit of a dull day for me, I guess. It's
We've added 2 extra pixels around the edge. Now if we go down, 1
yeah,
extra pixel.
not the
Now
best.
if we go 0. Now why might we do that? If we add some padding on
I guess whenever I worked, I've never really used DSA, but there are many problems out there. Let's just okay.
well, that's so that our kernel can operate on what's going on here in the corner, in case there's some information on the edges of our image. Now you might be thinking, Daniel, there's a whole bunch of values here. How do we know what to set them? Well, you notice that I've just copied exactly what is going on here. There's a 3 by 3 kernel. Bunch of values here. How do we know what to set them? Well, you notice that I've just copied exactly what is going on here. There's a 3 by 3 kernel. There's no padding on the image, and this
Let's see. Anyway, I have a lot of steps to go before I reach a point where I stream DSA. Anyways,
stride is just going 1 by 1. And so that's often very common in machine learning, is that when you're just getting started and you're not sure what values to set these values to, You just copy some existing values from somewhere and see if it works on your own problem.
Yeah.
And then if it doesn't, well, you can adjust them. So let's see what happens when we do that. So pass the data through the convolutional layer. So let's see what happens. Conv output equals conv layer. Let's pass it our test image. And we'll check the conv output. What happens? Oh no, we get an error. Of course we get a shape error, one of the most common issues of machine learning and deep learning. So this is saying that our input for the conv layer expects a 4-dimensional tensor, except it's got a 3-dimensional input size of 364. Now how do we add an extra dimension to our test image? Let's have a look. How would we add a batch dimension over on the left here? We can go unsqueeze 0. So now we have a 4-dimensional tensor. Now, just keep in mind that if you're running this layer, NNCOM2D, on a Pytorch version that is, I believe,
Where in your life you felt like DSA held you back? No, no, it's just it's one of those things which I just
they fixed this or
wanna
they changed
learn just for the sake of learning.
in Pytorch, what am I on? On a Pytorch version that is, I believe they fixed this or they changed it in Pytorch, that if you're running this layer, NNCOM2D, on a Pytorch version that is, I believe they fixed this or they changed it in Pytorch, what am I on? I think this Google Colab instance is on 1.10. I think you might not get this error if you're running 1.11, so just keep that in mind. Like this should work if you're running 1.11. But if it doesn't,
Yeah,
we'll unsqueeze here. And let's see what happens. Oh, look at that. We get another tensor output. Again, this is just all random numbers though, because our test image is just random numbers, and our conv layer is
Do Linux as in GNU plus Linux. More utility. Again, I've heard GNU. What was GNU again? Full. Oh, you mean
instantiated with random numbers. But we'll set the manual seed here. Now, if our numbers are different to what's on my screen, don't worry too much. Why is that? Because our conv layer is instantiated with
more
random numbers,
utility.
and our test image is
Or
just
try
random numbers as well.
out that operating system is what you say?
What we're paying attention to is the input.
Alright, yeah. I guess, yeah. I do know enough Linux to, I mean, Linux commands to survive. But yeah.
Input and output shapes. Do you see what just happened? We put our input image in there.
What is PWLS is for like going in, checking files in a directory. What is PWD?
And now, because we've set out channels to be 10, we've got 10, and we've got 62, 62, and this is just the batch size, it just means one image. So essentially, our random numbers, our test image, have gone through the convolutional layer that we created, have gone through this mathematical operation with regards to all the values that we've set. We've put the weight tensor, well, actually, Pytorch created that for us.
A lot of numbers.
Pytorch has done this whole operation for us. Thank you, Pytorch. It's gone through all of these steps across. You could code this all by hand if you want, but it's a lot easier and simpler to use Pytorch. And it's done this, and now it's created this output. Now, whatever this output is, I don't know. It is random numbers, but this same process will happen if we use actual data as well. So let's see what happens if we change the values. Kernel size, we increase. Notice how our output has gotten smaller because we're using a bigger kernel to convolve. Across the image. What if we put this to 3.3 back to what it was and stride to 2? What do you think will happen? Well, our output size basically halves because we're skipping 2 pixels at a time. We'll put that back to 1. What do you think will happen if we set padding to 1? 64, 64. We get basically the same size because we've added an extra pixel around the edges. So you can play around with this, and in fact, I encourage you to do. This is what we just did. Padding 1. We just added an extra dummy 0 pixel around the edges. So practice with this. See what happens as you pass our test image, random numbers, through a COM2D layer with different values here. What do you think will happen if you change this to 64? Give that a shot, and I'll see you in the next video. Who's ready to step through the NN Max Pool 2D layer? Put your hand up. I've got my hand up, so let's do it together, hey? We've got 7.2. Now, you might have already given this a shot.
Right, yep, we have reached our goal for today. We finished almost 2 hours. Alright, perfect. I'm about to quit the stream now. Again, thank you, Aishwarya, for, joining me. Alright, yep, it's been a very nice talk, and I'll see you in the next one. What's the plan today? Plan as in, oh, you mean the plan for today? I don't know if you've been realizing this, but each day I'm finishing like 2 hours worth of content. What's the plan today? Work. Didn't get you what you meant. Oh, am I working on something after this? I'm not sure. I don't know. I haven't made a plan on what I'll be doing after this. Probably getting some rest and stuff. Yeah. I might. I'm not sure. I may or may not do another stream maybe later on. We'll have to see. Yeah, sure. That's something I have in the roadmap. Seriously, yeah. Um, I just need to build up enough skills and whatnot for it. Anyhow, I'll be logging off now. I will have to see what you are done with this. Sure thing, actually, yeah. Take care too. Alright, see ya. Bye. And yeah, take care, everyone. See you in the next one.